All right, today we're tackling one of the absolute cornerstones of machine learning, logistic regression. We're going to peel back the layers and really get into how it works, what makes it so useful, and how it learns to make smart calls when the answer isn't obvious.
So let's start with a super simple question, one that we all deal with. Just by looking at the temperature outside, can we predict whether I'm going to wear a coat? It sounds basic, but this is a perfect classic example of a classification problem, and it's going to help us understand everything.
So how are we going to figure that out? Well, here's our game plan for today. We'll kick things off by seeing why a simple line just won't work. Then we'll find a much better solution with something called the S-curve. After that, we'll dive into how the model actually learns, how we can keep it from getting too confident, and finally, how we can take this way beyond a simple yes or no.
Okay, first up, the problem with lines. Let's dig into why the most straightforward approach just kind of falls flat when you apply it to the real world.
Just think about our coat example. If it's freezing outside, you're wearing a coat. No question. If it's super hot, you're definitely not. But what about all those days in between? You know, that chilly autumn morning or a cool spring evening? The decision isn't just a sudden switch, right? It's a fuzzy gray area. And that is exactly the problem. A simple straight line, what we call a linear classifier, it just can't handle that fuzziness. It's too black and white. It draws a hard line in the sand and gives a hard yes on one side and a hard no on the other. It has absolutely no way of saying, I'm about 70% sure. It just doesn't get the concept of probability.
So, if a straight line isn't the answer, what is? Well, that brings us right to section 2, the S-curve solution. We need to find a shape that can actually embrace that real-world uncertainty. The big question we've got to answer is this: what kind of shape can actually model that gradual shift? We need something that can start down at 0 for a definite no, end up at 1 for a definite yes, and crucially, move between them in a nice, smooth curve. And boom, here it is. The answer is called the sigmoid function, and it's this really elegant S-shaped curve that is just perfect for the job. Its entire purpose is to take any number you throw at it, big or small, positive or negative, and just kind of squash it down so the output is always a value between 0 and 1. And what else lives between 0 and 1? Probability. It's a perfect match. And there you have it. I know it might look a little intense with all the symbols, but this simple formula is the powerhouse that creates that amazing S-curve. This is the mathematical heart and soul of logistic regression. Okay, so we've found the perfect shape, but how do we actually get that S-curve to bend and stretch to fit our specific data about coats and temperatures? Well, let's jump into section 3 and see how the model actually learns. At its core, a model is really just trying to do one thing: make as few mistakes as it possibly can. In machine learning, every time it gets something wrong, we call that loss. So the model's entire job is just to keep adjusting its S-curve until that loss, that total error, is as low as it can possibly go. And the main tool it uses for this is an amazing algorithm called gradient descent. The analogy here is fantastic. Just imagine that the model's error is a huge, hilly landscape. Gradient descent is like putting a ball on that landscape and just letting it roll downhill. It will always find the steepest path down, and eventually, it'll settle in the lowest point of the valley. And that lowest point, that's our minimum error. That's the best fit for our data. So that rolling downhill process is really just a simple repeating loop. First, it measures its current error, asks itself, how wrong am I right now? Then it figures out which direction is the fastest way downhill to reduce that error. It takes one small step in that direction, and then it just does it all over again, and again, getting a little bit better, a little bit smarter with every single step. Now there's a catch. A model can sometimes get too good at fitting the data it's seen. It basically memorizes the answers and becomes overconfident. And that brings us to our next section, preventing overconfidence. The solution here is a clever technique called regularization. You can think of it like a penalty system. We're telling the model, look, I want you to be accurate, but I'm also going to penalize you if you get too certain or make your S-curve too extreme. This basically forces the model to learn the general pattern instead of just memorizing, which helps it do a much better job on new data it's never seen before. So what you end up with is this constant tug of war. On one side, you have the data loss part, which is pushing the model to match the training data perfectly. But on the other side, you have regularization, which is pulling back and saying, hey, let's keep it simple so that we can handle new stuff we haven't seen yet. The key to a great model is finding that perfect balance between the two.
This isn't even a new idea. This is really just a modern take on a very old principle called Occam's razor, which basically says that if you've got a bunch of competing explanations, the simplest one is probably the best one. Regularization is just Occam's razor for algorithms.
All right, let's move on to our final section and see how we can build on this. We have totally mastered a yes or no problem, but what happens when there are more than just two possible answers? So imagine instead of deciding about a coat, we're trying to classify a picture. Is it a cat, a car, or a frog? The model might first spit out some raw scores. We call them logits, like these. I mean, car has the highest score, which is a hint, but these numbers by themselves don't really mean much. How do we turn them into something we can actually use?
For that, we bring in the sigmoid function's bigger, more powerful sibling. It's called the softmax function. And the idea is really simple. If sigmoid is what you use for 2 choices, softmax is what you use for 3 choices or 4 or 1,000. And check out what softmax does. It takes those weird raw scores and magically transforms them into a clean set of probabilities. Now the model can say, okay, I'm 87% sure it's a car, there's maybe a 13% chance it's a cat, and yeah, there's basically 0 chance it's a frog. And the most important part, all of those probabilities add up perfectly to 1. This whole process, this extension of our model, is called softmax regression. But really, it's just logistic regression that's been beefed up to handle multiple classes. It's the thing that turns those raw scores into useful probabilities and makes sure they all add up correctly. It's what makes our models so incredibly versatile. And that really completes our journey. I mean, think about it. We started with a simple, flawed straight line that could only give a hard yes or no. And we've built our way up to this sophisticated system that can handle tons of different categories and even express its answers in terms of how certain it is. That is a massive leap forward. And this leaves us with one last really fascinating question to chew on. We've built one of these powerful classifiers, but what would happen if we started stacking them? What if we took the output from one and fed it into another one, and then another one on top of that? Well, that very idea, stacking these layers, is the doorway that leads to the entire universe of neural networks and deep learning.